Introduction to Google Cloud VPC Packet Mirroring. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring Google Cloud VPC Packet Mirroring, a powerful network traffic monitoring capability that helps you analyze and troubleshoot your workloads at scale. Packet mirroring is fundamentally different from traditional flow logging because it doesn't just record metadata about connections. Instead, it creates complete copies of actual network packets, including their full payloads and headers, giving you deep visibility into what's really happening on your network. Think of packet mirroring as installing a security camera system for your network traffic. Just as security cameras capture everything happening in a physical space, packet mirroring captures all the data flowing through your virtual machines. This is incredibly valuable for security teams who need to detect threats that might span multiple packets, or for network engineers troubleshooting subtle performance issues that wouldn't show up in standard logs. The diagram on your screen illustrates how traffic flows through packet mirroring. At the top, we have your source virtual machines, which are the virtual machines whose traffic you want to monitor. These could be web servers, database instances, application servers, or any compute resources in your VPC. The arrow labeled traffic flow shows normal network communication happening to and from these virtual machines. This is the production traffic that needs to be monitored. Below that, we see packet mirroring performing its cloning operation. The arrow labeled mirrored traffic clone shows that packet mirroring creates exact copies of packets without interfering with the original traffic. This mirroring happens at the virtual machine level, not at the network infrastructure level, which is an important architectural distinction. At the bottom of the diagram, we have collector virtual machines receiving these mirrored packets. These are specialized instances running security analysis tools, IDS/IPS, or network monitoring software. The collector virtual machines receive all the mirrored traffic through an internal load balancer, which we'll discuss in detail later. The key point here is that your production virtual machines continue operating normally while complete copies of their traffic are sent to analysis tools. Mirrored sources configuration. When you configure packet mirroring, you need to specify which virtual machines you want to monitor. Google Cloud provides flexible options for selecting these mirrored sources, allowing you to choose the approach that best fits your operational model. You can select sources in 3 different ways, and these methods can be combined within a single policy. The first method is subnet-based selection. When you specify a subnet as a mirrored source, every virtual machine instance with a network interface in that subnet gets mirrored automatically. This includes both existing instances and any instances that are created in that subnet in the future. This approach is particularly useful when you want comprehensive monitoring of entire network segments. For example, if you have a subnet dedicated to database servers, you could mirror the entire subnet to monitor all database traffic without having to update your policy every time a new database instance is added. The second method uses network tags. Network tags are labels you can assign to virtual machine instances for organizational and policy purposes. When you specify a network tag in your mirroring policy, any instance with that tag gets mirrored, regardless of which subnet it's in. This is incredibly flexible for application-centric monitoring. For example, you might tag all your payment processing virtual machines with a payment processing tag, then create a mirroring policy targeting that tag. Now all payment processing instances are monitored, even if they're spread across multiple subnets or regions. The third method is direct instance selection, where you explicitly name specific virtual machine instances to be mirrored. This gives you precise control when you want to monitor specific instances without affecting others. This might be useful during troubleshooting when you want to focus on a particular problematic instance, or when you have specific compliance requirements for certain critical systems. Looking at the diagram on your screen, you can see how these 3 selection methods work. The top section shows a subnet containing 3 virtual machines. When you mirror by subnet, all three instances are automatically included. The middle section illustrates tag-based selection, where instances across different subnets but sharing the same tag are all mirrored together. The bottom section shows individual instance selection, where you have explicitly chosen specific virtual machines by name. An important aspect of this configuration is that you can combine these selection methods in a single policy. If a virtual machine matches any of your specified criteria, whether by subnet, tag, or instance name, it will be mirrored. This or sign logic gives you powerful flexibility. For example, you could create a policy that mirrors all instances in your production subnet, plus any instances tagged as high security, plus 3 specific instances running critical legacy applications. Traffic filtering capabilities. By default, packet mirroring captures all IPv4 traffic from your mirrored sources, which could result in enormous amounts of data being duplicated. To help manage bandwidth consumption and focus on relevant traffic, Google Cloud provides sophisticated filtering capabilities. These filters allow you to narrow down exactly what traffic gets mirrored, or expand mirroring to include IPv6 traffic. The first filtering dimension is the protocol. You can specify which layer 4 protocols you want to mirror. For example, you might only want to mirror TCP traffic because you're investigating a connection problem, or only UDP traffic if you're troubleshooting a domain name system issue. You can also mirror specific protocols like Internet Control Message Protocol for network diagnostics. The protocol filter helps you focus on the type of traffic relevant to your investigation. The second dimension is CIDR range filtering. This allows you to specify which source or destination IP addresses should be mirrored. For instance, you might only want to mirror traffic going to or coming from a specific external partner's IP range, or traffic destined for your database subnet. CIDR filtering works for both IP version 4 and IP version 6 addresses. This is particularly useful because, by default, packet mirroring only captures IP version 4 traffic. If you need to mirror IP version 6 traffic, you must explicitly specify an IP version 6 CIDR range filter. You can mirror all IP version 6 traffic by using a filter of 2:0, or mirror both all IP version 4 and all IP version 6 by using a comma-separated filter combining quad 0/0 and 2:0. The third dimension is traffic direction. You can choose to mirror only ingress traffic, only egress traffic, or both directions. This is valuable when you know your issue is specifically related to incoming or outgoing traffic. For example, if you're investigating a data exfiltration concern, you might focus exclusively on egress traffic to reduce the volume of mirrored data. Looking at the diagram on your screen, you can see how filters work to narrow traffic scope. At the top, we have all traffic, which represents the complete traffic flowing through your source virtual machines. Below that, the protocol filter narrows this down, perhaps to only TCP traffic. Then the CIDR filter further narrows the scope, maybe to traffic involving a specific IP range. Finally, the direction filter reduces it even more, perhaps to only egress traffic. The result at the bottom is mirrored traffic, which is the subset of packets that actually gets cloned and sent to your collectors. An important consideration is that you can combine these filters. For example, you could create a filter that mirrors only TCP protocol traffic, going to the 10.0.0.0/8 CIDR range, in the egress direction. This combination might capture all traffic from your virtual machines to your internal database servers. The more specific your filters, the less bandwidth is consumed by mirroring, and the more focused your analysis becomes. Key properties and constraints. Before implementing packet mirroring in production, you need to understand its key properties and constraints. These aren't arbitrary limitations, but are architectural decisions that affect how you design your monitoring infrastructure. Being aware of these properties will help you avoid configuration mistakes and plan for scale. First, let's address regional requirements. All mirrored sources must be in the same project, VPC network, and Google Cloud region. You cannot create a single policy that mirrors instances in US Central 1 and instances in Europe West 1. This regional constraint exists because packet mirroring operates at a regional level within Google Cloud's infrastructure. The collector destination must also be in the same region as the mirrored sources. This keeps the mirrored traffic local to the region, minimizing cross-region bandwidth costs and latency. However, the collector destination has some flexibility. While it must be in the same region, it can be located in a different VPC network than the mirrored sources, as long as those networks are connected via VPC network peering. This enables centralized monitoring architectures where you have a dedicated security VPC with your collector infrastructure, and you peer it with your production VPCs to mirror their traffic. An important architectural constraint is that you cannot mirror and collect traffic on the same network interface of a virtual machine instance. Why? Because this would create a mirroring loop. Imagine a collector instance whose traffic is also being mirrored. The original traffic would be cloned. The clone would be sent to the collector, but that cloned traffic would itself be new traffic that would get cloned again, creating an infinite loop. To prevent this, Google Cloud enforces that source and collector interfaces must be separate. For Google Kubernetes Engine users, there's a specific consideration. If you want to mirror traffic passing between pods on the same GKE node, not just traffic leaving the node, you must enable intra-node visibility for your cluster. Without this setting, internal pod-to-pod traffic on the same node isn't visible to packet mirroring because it doesn't traverse the network interface in a way that can be intercepted. Bandwidth consumption is another crucial property to understand. Packet mirroring clones traffic, which means it doubles the egress bandwidth from mirrored instances. If an instance normally has 1 gigabit per second of ingress and 1 gigabit per second of egress, after mirroring it will have 1 gigabit per second of ingress but 3 gigabits per second of egress. That's the original 1 gigabit egress plus 2 gigabits of mirrored traffic, mirroring both the original ingress and egress flows. This increased bandwidth consumption has cost implications and can approach the network bandwidth limits of your virtual machine instance types. There are also quota limits to be aware of. Each project has a maximum number of packet mirroring policies you can create. For each policy, you can specify up to 5 subnets, 5 network tags, or 50 individual instances as mirrored sources. The maximum number of filters per policy is 30, calculated as the number of IP address ranges multiplied by the number of protocols. So you could have 30 ranges with one protocol, but not 30 ranges with 2 protocols, as that would be 60 filters exceeding the limit. Application performance monitoring. Beyond security, packet mirroring is invaluable for troubleshooting application performance issues. Network engineers often face situations where applications report problems, but traditional logging does not reveal the root cause. Being able to see exactly what is going over the wire provides insights that application logs simply cannot deliver. The performance troubleshooting workflow shown in the diagram illustrates this process. At the top, we have application virtual machines running your business applications. Users might be reporting slow response times, intermittent failures, or other performance problems. Below that, packet mirroring creates copies of all network traffic to and from these application virtual machines. These mirrored packets flow to network analysis tools, shown in the middle of the diagram. These are specialized applications that can examine packet timing, identify retransmissions, detect packet loss, and measure actual network latency. One specific problem these tools can detect is packet loss. When packets are dropped somewhere in the network path, TCP will retransmit them. By examining mirrored traffic, network engineers can count retransmissions and identify lossy network paths. High retransmission rates directly impact application performance, causing slow response times that frustrated users report. Another issue these tools can identify is TCP resets. A TCP reset is an abrupt connection termination, and unexpected resets often indicate application errors, firewall interference, or network configuration problems. By seeing the actual packets, engineers can determine whether resets are being sent by the application, by a middle box like a firewall, or by the remote endpoint. This visibility narrows down where to focus troubleshooting efforts. Moving down the diagram, we see protocol analysis being performed. This involves examining how applications are using network protocols. For example, an application might be configured to use HTTP 1.1 when HTTP 2 would provide better performance. Or an application might be making many small database queries when a few larger queries would be more efficient. Protocol analysis of mirrored traffic reveals these inefficiencies that wouldn't be apparent from application logs alone. At the bottom of the diagram, we see performance metrics being generated from the mirrored traffic analysis. These metrics might include average response times, 95th percentile latencies, error rates, connection establishment times, and throughput measurements. These quantitative metrics help engineers understand whether changes to the application, network, or infrastructure are actually improving performance. You can establish baselines from mirrored traffic, then compare current performance to those baselines to detect degradation before users complain. For real-time interactive applications like voice over IP or remote desktop connections, packet mirroring is especially valuable. These applications are sensitive to network jitter, packet loss, and latency. By analyzing mirrored traffic in real time, network engineers can identify issues affecting user experience, such as excessive packet resends, out-of-order delivery, or connection instability. This level of analysis isn't possible with simple flow logs that only show that a connection existed, not how well it performed. Same network topology deep dive. Let's examine the simplest packet mirroring topology in detail, where both mirrored sources and the collector destination exist within the same VPC network. This configuration is straightforward to implement and understand, making it ideal for organizations just getting started with packet mirroring or those with simpler network architectures. Looking at the diagram on your screen, we can see the complete architecture of a same network deployment. At the top left, we have the mirrored subnet containing your source virtual machines. These are the instances whose traffic you want to monitor. They could be web servers, application servers, database instances, or any other workload running in your VPC. Moving across the top, we see various traffic destinations that your mirrored virtual machines communicate with. The Internet represents external traffic, such as users accessing your web applications or your applications calling external APIs. The on-premises network represents connectivity through Cloud VPN or Cloud Interconnect to your corporate data center. Google Services represents traffic to Google Cloud APIs and services. All of this traffic, both ingress and egress, is subject to mirroring. In the center of the diagram, we see the packet mirroring policy, which is the configuration object that ties everything together. This policy specifies that instances in the mirrored subnet should have their traffic cloned. The policy contains the selection criteria we discussed earlier, the filtering rules if any are applied, and a reference to the collector destination. At the bottom of the diagram, we see the collector infrastructure. The internal load balancer is the entry point for mirrored traffic, configured specifically for packet mirroring. Behind it sits the collector instance group, containing the actual collector virtual machines running your analysis software. The mirrored traffic flows from the source virtual machines, through the packet mirroring policy which clones it, and then to the internal load balancer which distributes it across the collector instances. The advantage of this same network topology is simplicity. Everything exists in one VPC network, so there are no peering relationships to manage, no cross-project permissions to configure, and network connectivity is straightforward. You create the packet mirroring policy in the same project that owns the VPC, specify sources within that VPC, and point to a collector destination also in that VPC. This keeps network traffic paths simple and reduces the complexity of troubleshooting. However, this topology has limitations. If you have multiple VPC networks or multiple projects, you would need separate collector infrastructures in each VPC, or you would need to implement one of the more advanced topologies we'll discuss in upcoming slides. For single VPC environments or proof-of-concept deployments, though, the same network topology is often the best choice. Shared VPC Collector in Service Project. Shared VPC is a Google Cloud feature that allows multiple projects to share a common VPC network. In a shared VPC setup, there's a host project that owns the VPC network and subnets, and service projects that can use those shared network resources. This organizational model aligns well with enterprise structures where a central IT or networking team manages network infrastructure, while application teams operate in their own projects. In the topology shown in the diagram, we're looking at a specific shared VPC scenario where the collector destination is located in a service project. At the bottom of the diagram, we see the host project containing the shared VPC network. This VPC network has multiple subnets, and these subnets can be used by both the host project and attached service projects. At the top left, we see the service project for the collector. This project contains the collector instance group, which includes the actual virtual machines running your monitoring software. These collector instances are using a collector subnet from the shared VPC network. Even though the collector instances exist in the service project, they're using network resources from the host project, which is how shared VPC works. At the top right, we see the mirrored sources. The diagram shows instances in the mirrored subnet, which is also part of the shared VPC network. These source instances could be in the host project, in the collector service project, or in other service projects that are not shown. The key point is that all these instances are using the same underlying VPC network. In the center, we see the packet mirroring policy. This policy could be created in either the service project containing the collector or in the host project. The flexibility of where to create the policy is one of the advantages of shared VPC. If the application team operating the service project wants to monitor their own instances and has provisioned collector infrastructure in their project, they can create the policy themselves. Alternatively, the central networking team in the host project could create policies to monitor instances across all service projects. The mirrored traffic flow is shown with arrows. Traffic from mirrored source instances is cloned by the packet mirroring policy, then sent to the internal load balancer, which distributes it to the collector instances in the service project. All of this happens within the shared VPC network, so there's no need for VPC peering or other cross-network connectivity mechanisms. The IAM requirements for this topology depend on who is creating the policy. If a user in the service project creates the policy, they need the compute packet mirroring user role in the service project where the collector destination is located, and they need the compute packet mirroring admin role on the mirrored sources. If a user in the host project creates the policy, they need similar permissions but scoped appropriately to the host project resources and the service project collector destination. Multi-interface virtual machine instances. Some virtual machine instances in Google Cloud can be configured with multiple network interfaces, allowing them to connect to multiple VPC networks simultaneously. This capability is useful for network appliances, security tools, or applications that need to bridge multiple networks. However, packet mirroring of multi-interface instances requires special consideration because of how packet mirroring policies are scoped. In the diagram on your screen, we see a virtual machine instance with multiple interfaces at the center. This instance has 3 network interfaces, each connected to a different VPC network. On the left, interface 1 connects to VPC network A. At the top, interface 2 connects to VPC network B. On the right, interface 3 connects to VPC network C. Each interface has its own IP address and routes traffic for its respective network. The crucial constraint with packet mirroring is that a single policy can only mirror resources from one VPC network. This is because the packet mirroring policy is associated with a specific network, and it monitors traffic on network interfaces connected to that network. Looking at the diagram, if you want to mirror traffic on interface 1, you would create a packet mirroring policy in VPC network A. This policy can only read and mirror traffic flowing through interface 1. If you also want to mirror traffic on interface 2, you cannot simply add it to the existing policy. Interface 2 is connected to VPC network B, which is a different network. You would need to create a separate packet mirroring policy in VPC network B specifically for interface 2. Similarly, mirroring interface 3 would require a third policy in VPC network C. This means that fully mirroring a multi-interface instance requires creating multiple packet mirroring policies, one for each network interface you want to monitor. Each policy would potentially send mirrored traffic to different collector destinations, or if you want centralized collection, you would need to set up VPC peering or shared VPC arrangements so that all the policies can send traffic to a common collector infrastructure. The diagram shows each interface with an arrow pointing to its respective packet mirroring policy, illustrating that each interface requires its own policy. Policy for network A handles interface 1, policy for network B handles interface 2, and policy for network C handles interface 3. Each policy independently clones packets and forwards them to its configured collector destination. This architecture has implications for bandwidth consumption as well. If you mirror all three interfaces, the instance will be sending mirrored traffic for all three interfaces, significantly increasing egress bandwidth. You need to consider whether you actually need to mirror all interfaces or if monitoring one or two is sufficient for your use case. The practical application of this often comes up with network virtual appliances that have interfaces in multiple networks. For example, a firewall appliance might have an interface in a trusted internal LAN and another interface in an untrusted DMZ network. If you want comprehensive security monitoring, you might choose to mirror both interfaces to see traffic on both sides of the firewall, giving you complete visibility into what the firewall is processing. Bandwidth consumption impact. One of the most important operational considerations with packet mirroring is its impact on network bandwidth. Because mirroring creates complete copies of packets, it fundamentally doubles the amount of data that needs to be transmitted from your mirrored instances. Understanding this bandwidth multiplication effect is crucial for capacity planning and cost estimation. The diagram illustrates the bandwidth impact with a concrete example. At the top, we see an instance before mirroring in its normal operating state. The arrow labeled 1 gigabits per second ingress shows incoming traffic to the instance, perhaps users accessing a web application or data being loaded into a database. The arrow labeled 1 gigabits per second egress shows outgoing traffic, maybe responses being sent to users or data being written to cloud storage. In this pre-mirroring state, the instance is handling a total of 2 gigabits per second of traffic, 1 gigabit in each direction. This is straightforward and matches how we typically think about network capacity. The instance consumes ingress bandwidth receiving data and consumes egress bandwidth sending data. Now let's look at the bottom portion showing the instance after mirroring is enabled. The ingress side hasn't changed. The arrow still shows 1 gigabit per second ingress. Packet mirroring doesn't create copies of the ingress packets as they arrive. It mirrors them after they've been received by the instance. So from an ingress perspective, bandwidth consumption is the same. The egress side tells a different story. We now see an arrow labeled 3 gigabits per second egress. Where does this 3 gigabits come from? Let's break it down. First, there's the original 1 gigabit per second of egress traffic, the normal outbound traffic the instance needs to send. This traffic still goes to its intended destination exactly as before. Second, there's 1 gigabits per second of mirrored egress traffic. This is a clone of the original egress traffic being sent to the collector infrastructure. When the instance sends data out, packet mirroring creates copies and transmits those copies to the collectors. Third, there's 1 gigabit per second of mirrored ingress traffic. Wait, what? This might seem counterintuitive, but remember that when the instance receives ingress traffic, that traffic needs to be mirrored too. The mirrored copies of the ingress traffic have to be transmitted out of the instance to reach the collectors. From the instance's perspective, sending mirrored copies of received traffic counts as egress bandwidth. So the total is 1 gigabits per second original egress, plus 1 gigabits per second mirrored egress, plus 1 gigabits per second mirrored ingress equals 3 gigabits per second total egress. The instance now needs 3 times its original egress capacity. This has several practical implications. First, you need to ensure your instance types have sufficient network bandwidth. Google Cloud instances have network bandwidth caps that vary by machine type. If your instance is already near its bandwidth limit, enabling mirroring could cause it to hit that limit and experience network throttling. Second, this affects costs. Google Cloud charges for egress bandwidth, especially when traffic leaves a zone or region. The mirrored traffic traveling from your source instances to collector instances is subject to these charges. If your collectors are in a different zone, you'll pay inter-zone egress costs for the mirrored traffic. This is why using filters to narrow the scope of what gets mirrored can provide significant cost savings by reducing the volume of mirrored data. Pricing considerations. Understanding the cost structure of packet mirroring is essential for budgeting and for making informed decisions about what traffic to mirror and how to architect your collector infrastructure. Packet mirroring incurs charges from multiple sources, and the total cost can be significant at scale. The diagram breaks down the different cost components. Starting at the top, we have data processing charges. This is the primary cost of packet mirroring itself. Google Cloud charges you based on the amount of data that is processed by the packet mirroring system. Processing means the creation of mirrored packet copies. Every gigabyte of traffic that gets mirrored incurs this data processing charge. The pricing is published on Google Cloud's VPC pricing page under the packet mirroring section. Below that, we see egress traffic costs. Remember from our bandwidth discussion that mirrored traffic is transmitted from source instances to collector instances. This transmission is egress traffic, and Google CP charges for egress based on where the traffic goes. If your collector instances are in the same zone as your source instances, the inter-zone egress charge does not apply. However, if collectors are in a different zone, you pay for traffic crossing between zones. If collectors are in a different region, you pay higher inter-region egress charges. The arrow points from egress traffic costs to the higher charges notation, emphasizing that cross-zone and cross-region mirroring increases costs substantially. In the middle of the diagram, we see compute costs for collectors. Your collector instances are regular Google Compute Engine virtual machines, and you pay standard compute pricing for them. This includes the machine type costs based on vCPUs and memory, any attached persistent disks, and other typical virtual machine charges. The arrow shows these costs are ongoing for as long as the collectors run. If you're running large or high-performance collector instances to handle significant traffic volumes, these compute costs can be substantial. Next, we have load balancer charges. The internal load balancer that serves as the entry point for mirrored traffic incurs its own costs. Internal load balancers have forwarding rule charges and data processing charges based on the amount of traffic they handle. Since all your mirrored traffic flows through this load balancer, the charges scale with your mirrored traffic volume. At the bottom, we see optional storage costs. This isn't a direct charge from packet mirroring itself, but rather a cost that many organizations incur when they store captured packets for forensic analysis or compliance purposes. If your collector instances write packet captures to cloud storage, you pay storage costs for that data. Depending on your retention requirements, this could become a significant ongoing expense. The diagram shows all these cost components flowing together, illustrating that the total cost of packet mirroring is the sum of multiple charges. To optimize costs, you have several levers. First, use filters to reduce the volume of traffic being mirrored. If you can narrow mirroring to only relevant traffic through protocol, CIDR, or direction filters, you reduce data processing charges proportionally. Second, Keep collectors in the same zone as sources when possible to avoid inter-zone egress charges. Third, right-size your collector instances. Use auto-scaling in your instance groups so you're only running the capacity you need. Fourth, consider your packet storage strategy carefully. You might store packets in nearline or cold-line storage classes if you only need them for occasional investigation rather than keeping everything in standard storage. Best practices and recommendations. As we conclude this presentation on Google CP VPC packet mirroring, let's review the key best practices and recommendations that will help you implement packet mirroring effectively, securely, and cost-efficiently in your environment. Looking at the diagram, we see best practices organized into 4 key categories. The top section covers design considerations. First, start with a clear use case. Don't enable packet mirroring just because it's available. Identify specific security requirements, compliance needs, or troubleshooting objectives that packet mirroring will address. This clarity helps you configure mirroring appropriately. Second, use filters aggressively. The default behavior of mirroring all traffic can generate enormous data volumes and costs. Apply protocol filters to mirror only TCP if that's what you need. Use CIDR filters to focus on specific network segments. Use direction filters if you only need ingress or egress. Every filter that narrows your scope saves bandwidth and money. Third, plan your topology based on your organizational structure. If you have a central security team, use peered or shared VPCs topologies with centralized collectors. If teams are independent, same network topologies might be simpler. Match your packet mirroring architecture to how your teams actually operate. Fourth, right-size your collector infrastructure. Monitor the actual traffic volumes reaching your collectors and adjust instance group size accordingly. Use auto-scaling to handle traffic variations. There's no point running excess capacity that sits idle. The second section covers security practices. First, secure collector instances carefully. They receive copies of potentially sensitive traffic, so they should be in isolated subnets with strict firewall rules. Only allow necessary management access. Consider using shared VPC or network peering to keep collectors in a separate security zone. Second, use IAM roles properly. The Compute Packet Mirroring Admin role grants broad permissions, so assign it carefully. Use Compute Packet Mirroring User role for teams that should be able to use collector destinations but not modify mirroring policies. Follow the principle of least privilege. Third, protect stored packet captures. If you're writing captured packets to cloud storage, use appropriate access controls, encryption, and lifecycle policies. Consider regulatory requirements for how long packet data must be retained and when it must be deleted. The third section addresses operational practices. First, monitor collector health continuously. Your collectors are critical infrastructure for security monitoring. Set up alerting if collector instances become unhealthy or if the load balancer fails health checks. You don't want to discover your monitoring isn't working during an actual security incident. Second, test your packet mirroring configuration regularly. Generate known traffic patterns and verify they appear in your collector systems as expected. This validates that your policies, filters, and collector infrastructure are working correctly. Third, document your policies thoroughly. Record why each policy was created, what it is monitoring, who requested it, and any specific filter settings. This documentation is invaluable when troubleshooting or when conducting security audits. The bottom section covers cost optimization. First, review your mirroring policies regularly. Traffic patterns change over time. A policy that was critical 6 months ago might be monitoring traffic that no longer exists. Deactivate or delete unnecessary policies. Second, monitor costs closely. Google Cloud's billing reports can break down packet mirroring costs by project and resource. Track these costs against your security budget and investigate any unexpected increases. Third, use committed use discounts for collector virtual machines if you know you'll be running packet mirroring long term. The sustained use discounts can reduce compute costs significantly for stable, long-running workloads. Thank you for your attendance. Please consider subscribing to the channel and liking this video.